1, 2, and 3 on page 177 of module 6. First question is pretty straightforward. The difference between single and double displacement reaction. First of all, we use the activity series of metals for single displacement reactions or for halogens, and then for double displacement we use the solubility table as shown here to predict the states. And then the general chemical equations are different. So we have A plus BC gives me, if it's a metal replacing a metal, AC plus B. And again, you'd use your activity series. Halogens look a little different, and we saw that in the previous solution video. For double displacement reactions, it would be AB, so a metal, non-metal, replacing or switching dance partners with a metal and a non-metal. So A changes with C to become AD, and then B is the non-metal, so C goes first. C is the metal to create CB. And then of course you use this table to predict the states. In question 2, we want to classify the reactions as being either single or double, so I'm just going to write S or D. This one, it follows this pattern, so of course it is going to be double displacement. And you can see the states here as predicted by the solubility table. This one is single displacement because it follows the pattern above. I should call these 1 and 2. Follows the pattern 1, where I have one element as a metal trying to replace this metal, and we would use activity series to determine that. Here I've got 2 compounds and then 2 compounds. It follows this pattern, so it is double. And then this one is, of course, our halogens. So yes, this halogen is going to replace this halogen because it is more reactive on the halogen activity series to create ammonium chloride. So this is single displacement. Now in question 3, I've already written down the compounds, but I can show you how to get to them. You need your polyatomic ion sheet, and in this case I just used lead 2. It is a multivalent metal, but we would find sulfate. Sulfate's over here, it's a 2 negative. So if lead, in this case if we're using 2 positive, you just use your crisscross rule and then reduce, they're both 2s, to give a 1-to-1. And now we have to look up lead sulfate. So remember, we're working backwards. Sulfate is here in the anions, and you have to ask yourself, does it fall under most? That doesn't give us enough information. So then I'm going to continue on and find lead 2 here, and it is low solubility. So lead sulfate in water is going to form a solid because it is low solubility. Now for B, it's ammonium phosphate. Ammonium is our positive polyatomic ion with a 1+ charge, and phosphate is here with a 3 negative charge. So again, these are all ionic. Which means that we use our crisscross rule, and we have to use brackets for polyatomics. So it becomes ammonium with a 3 after it, and then phosphate. So again, find phosphate, which is here, and then ammonium, which is here. So when we combine these two and go across, it has a high solubility. So this is going to be aqueous. Calcium sulfate. I've already covered what sulfate is with a 2 negative charge. Calcium is in group 2 with a 2 positive. So once you crisscross, it then reduces to be a 1-to-1. So we find sulfate. And again, most does not give us enough information. So let's see if calcium falls under the low solubility, which it does. So calcium sulfate is going to form a solid in solution. Now I crisscross here with aluminum and sulfate. Aluminum is in group 13. It wants to donate 3 electrons. Sulfate, again, can only accept 2 electrons according to our polyatomic ion table. So once we crisscross, you have to apply the brackets outside of sulfate with the 3. So it becomes Al2SO43. So then go to sulfate, and could be most. We're not sure. So I'll keep going, and aluminum is not silver, lead 2, calcium, barium, strontium, or radium, which means that it falls under the most category and is going to be aqueous. So this one is going to be AQ. Calcium phosphate with the crisscross. Calcium is in group 2. Phosphate has a 3 negative charge, so Ca2 plus. Crisscross, apply the brackets, it doesn't reduce anymore, becomes Ca3PO42, so find phosphate. Calcium is in group 2, so it doesn't fall under group 1, and it is not ammonium, so it falls under most, which means that low solubility for calcium phosphate, and it would form a solid in water. So barium sulfate, barium's in group 2, sulfate has a 2 negative charge, crisscross the 2 of those things and reduce. And of course, we now need to use our lots of sulfate in this group. So sulfate's here, barium is here, and it is a low solubility, so it is in fact S. Now let's check ammonium carbonate. Ammonium, again, is our only single or positive polyatomic ion, so it's a 1+ charge. Carbonate is, of course, we would just look to see, and it is a 2 negative charge. So once we crisscross those things, you have to apply the brackets to the ammonium, because we need 2 ammoniums to accept those 2 electrons, and then it becomes here NH4 with a 2 outside and carbonate. So you look to carbonate, and of course ammonium is here, so it has a high solubility, meaning that this would be aqueous. That looked like 2 Q's. Aqueous in solution. And finally, calcium carbonate, pretty straightforward. Calcium being in group 2. Carbonate has a 2 negative charge. According to our polyatomic ion table, crisscross and reduce, and it becomes calcium carbonate. So find, here is carbonate, and of course calcium is not in group 1. It is not ammonium, so it falls under the most category, which means low solubility, and this is indeed going to be a solid. We predicted the products for each of those. So again, we're just switching dance partners. For A, zinc will switch with potassium, so it becomes zinc hydroxide, potassium chloride, and you can go over how to predict those ionic compounds and crisscross rule. So then from there, you just have to predict the states. So I have to find hydroxide with the anions, and then figure out if zinc is in group 1. If it's ammonium, strontium, barium, thallium, it's not. So it's in most. So zinc will have the solid symbol beside it, because you go down the group and zinc falls here, and then line it up, meaning it has low solubility for zinc. So you'd put S beside. Now let's test chlorine with potassium. So it could be in most. Chlorine's here, and it says silver, lead, thallium, mercury 2, mercury 1, and copper 1. So potassium does fall in the high solubility category, so you put AQ beside it. And I've already balanced all of these equations. So again, I'm not going to go over the ionic naming. We should know this already. But for B, nickel is going to replace or switch with the metal sodium. So it becomes nickel carbonate and sodium nitrate. Nitrate is your friend. Everything is going to be aqueous with nitrate. In the product side, as you can see, all have high solubility versus none here. So you can automatically add that. So let's test carbonate. Carbonate, when paired with nickel, it's not in group 1 and it's not ammonium, so it falls under the most, which means low solubility. So this one is going to be a solid. When we are combining these two compounds in a beaker, you are going to get a precipitate formed and an aqueous sodium nitrate just floating around as spectator ions. So barium hydroxide and potassium sulfate becomes barium sulfate and potassium hydroxide. So let's test sulfate, which is here. And barium does indeed fall under the low solubility category, so it is going to have an S. Whereas hydroxide, potassium is in group 1, so it is in the high solubility category, so it gets an aqueous beside it. Iron 2 sulfate and potassium phosphate. So iron is going to switch with the potassium and form iron 2 phosphate, whereas potassium will be potassium sulfate. Now let's check phosphate. And iron 2 is not in group 1, nor does ammonium, so it falls under the most category. It's low solubility, so it gets an S beside it. Whereas sulfate, this is sulfate, SO4 2 negative. Potassium is in the most, it's in high solubility because it's not silver, lead, calcium, barium, strontium, or radium, so it is most and gets a Q. Remember, it's an either or question. Now, E, F, and G are special cases outlined on page 176 of your bookshelf. So you would have to then go to that page and read about double displacement reactions that produce gases and or are unstable, or neutralization reactions. So in the very first one, it's zinc sulfide. And it says when we are dealing with an acid to a sulfide compound, their example is potassium sulfide, but ours is an acid, hydrochloric acid with zinc sulfide. So in this case, the double displacement reaction occurs. This is acting as a metal, so zinc goes here to form with chlorine, and then you have your H2S compound being formed with the hydrogen acting as the metal. So I already added in the states, and I've already balanced this thing because H2S, hydrogen sulfide gas, is formed under these conditions, which is a sulfide with an acid to give me, and then this is also going to be an aqueous compound formed. The second case is included in the table 2 on page 176, where when you have a carbonate with an acid, this is nitric acid, you will produce carbon dioxide as well as water. So it's kind of similar to our neutralization reaction, where calcium is going to replace hydrogen here to make calcium nitrate. That is aqueous. That's an easy one because we know our nitrates form aqueous solutions. And then carbon dioxide, this is just in a pattern, is a gas, and water is a liquid. So I've talked about this in previous videos. The final one is sulfite. This is magnesium sulfite, and again, this is with an acid. So from table 2, when you've got sulfites with acids, you get sulfur dioxide formed as a gas and water and a liquid. So this becomes magnesium chloride because it displaces hydrogen as an aqueous solution, and we have our gas and liquid.